So this is the last lecture in chapter 4. We're going to be looking at the greatest common divisor and the least common multiple, which are concepts that will be somewhat familiar to most students. The greatest common divisor is just the largest number that I can divide something by. So if I have groups of things, like a marching band has so many rows, right, they divide their marchers into, I'm looking for the largest number of rows that would work to group them together. So eventually, if I have too large of a divisor, I'm not going to be able to group them all together in their rows. So the number of columns for this example must divide both 24 and 30, which would be 1, 2, 3, and 6. Since the largest number is 6, that's going to be the greatest of these numbers. The first band would have 6 columns with 4 members in each column, and the second band would have 6 columns with 5 members in each column, because I was looking at the commonality between those two groups. So the greatest common divisor would be the greatest common factor. We're looking at numbers that divide both into A and B. So this is an example of a hands-on way to show this. And we can use these rods. If I'm looking at the greatest common thing is 6 and 8, using the 6 rod and the 8 rod. Find the longest rod so that we can use multiples of that rod to build both the 6 and the 8. So I can use 2 rods, and that's the largest one I can build that will fit on both, because the 3 rods will fit on one, but not the other. And the same thing applies true. So basically, this is having your students investigate the largest value you could divide by subdividing these rods into smaller groups. If you have access to rods, this is great. If you don't have access, that's okay. There's other methods. Another method would be to list all the members of the divisors of the two numbers, okay? Then pick who's in common, and then pick the biggest one, because something students often forget is if it's not divisible by both numbers, it can't be the greatest common factor. So if I look at 20 and 32, I would list all the factors of 20 out, list all the factors of 32 out. I'm going to indicate which ones are the same, and I'm going to pick the greatest one, which would be the number 4. So that matching up process is really important to help students. I could also build on what we did last module, and I could use some prime factorization. I could look at numbers like 4 and 9, whose greatest common divisor are 1 and are relatively prime, because 4 has the factors 1, 2, and 4. 9 has the factors 1, 3, and 9, and the only thing they have in common is 1. So we call those to be relatively prime. So let's find each of these. If I do 108, I can prime factor that down into 2 squared times 3 cubed. If I do 72, I can prime factor that down into 2 cubed, 3 squared. So if I look at this, I know 2 cubed times 3 squared is going to be 36. So, 2 squared times 3 cubed. Now, where does that come from? Because you have to take the lowest exponent from each group. So here, 2 squared is the lowest exponent, and this is 2 cubed, so I have to pull the squared. Then 3 squared is the lowest one, so I have to pull that one over here. If I'm looking at 0 and 13, the greatest common factor would be 13, because nothing goes into 0, or everything can be multiplied to get 0, depending on how you want to look at it. And then you're looking at factors of 13. So here are some other examples continued. If I'm looking at the factors of x, where it's 2 cubed times 7 squared times 11 times 13, and then y, I have this factor. So I'm going to pull everybody who's in common. So there's a common factor of 2, lowest exponent comes. Common factor of 7, lowest exponent comes. Common factor of 13. And then I multiply them all out to get the answer. So I apply that same process to D and E. I'm just looking at what values do they have in common in the prime factorization, and I'm taking the lowest exponent. And then the last one, they have nobody in common, so I don't have a greatest common divisor. Here's the calculator method. If you have this calculator key, it will help you find it. You're not required to buy a calculator for this course, but it may be that you're teaching this math course in a classroom with one of these calculators, and you could do this. We aren't really going to be doing this, though. So we're going to look at the Euclidean algorithm method next. If A and B are any whole numbers greater than 0, and A is greater than or equal to B, where R is the remainder when A is divided by B. So what does all that mean? Let's look at what that actually means. Finding the greatest common divisor of two numbers by repeatedly using the theorem above until the remainder is 0 is going to be the Euclidean algorithm. So I'm just going to constantly keep working on getting those divisors done, and then looking at, is there a remainder when I do those divisors? So here is the method. This is assuming we don't know if something is divisible by a number. So basically, we're checking to see if it's divisible by, say, 3. If the remainder is 0, then yes, it's divisible. If the remainder is not 0, then it's not going to be divisible by that number. So let's see how this works in action. So let's take this and divide it by 2,300 goes into this factor. So when I look at this, I'm going to go into this and I'm going to say, okay, well, 2,300 can go into 9,200. That's the closest we can get without, having a remainder, without having a negative remainder or something like that. So it's 4. And that's what we're going to be looking at, that's the answer. And if it's the greatest common factor of these two numbers, then it's also going to be the greatest common factor of these two numbers. So that then I'm going to find another one, and I get that the greatest common factor of the second Euclidean algorithm is equal to this one from the remainder process. And then I'm going to do it again and again. And ideally, you would just keep going in that method. So the greatest common divisor is 92. So basically, what you're seeing here is you're seeing us do some repeated things with that remainder. So the remainder of 1564 is going to be too large to try and figure out. So I'm going to take that remainder out and divide that into what I was originally dividing the 2300. Once I do that, I'm going to flip, same here. The 736 comes out, the 1564 goes in, and then the 92 comes out, the 736 goes in, and that's as far as I can go because I get a remainder of 0. And once you get the remainder of 0, you have to stop. So this is a repeated division process to help you find the greatest common divisor for very large numbers. A calculator with an integer division feature can be used to perform the Euclidean algorithm. So if you have this feature, this int division feature, you could do it. Or if you have it where your calculator will show you a remainder, which is not a common feature, but on the off chance you happen to get one of the lucky ones that does, this is what you could do. So here's another example to find the greatest common denominator. Any common divisor of the three numbers is also a common divisor of any two of them. So I'm looking at the greatest common divisor of the three numbers can't be bigger than any two of them. So if I look at this, I cannot be greater than 1, so it must be equal to 1 because I don't have any common factors. The greatest common divisor of any two consecutive whole numbers, this is so like 67, 68, would be 1, always. So if you have two consecutive whole numbers, the greatest common divisor is 1. And 1, while it is not prime or composite, it does count as a greatest common divisor. And that's something that students will sometimes get flipped when they're trying to remember things. Hot dogs are usually sold 10 to a package, while hot dog buns are sold 8 to a package. What is the least number of packages you must buy so you have an equal number of hot dogs and hot dog buns? So I have multiples of 10 and I have multiples of 8. So basically, they're really asking me to find the least common multiple. So I kind of start listing them out. So multiples of 10 or multiples of 40 would be 40, 80, 120. So I will have the same number of hot dogs and buns by buying 4 packages of hot dogs and 5 packages of buns because I'm going to have multiples of 10 and multiples of 8, and that's where they intersect, is at 40. So a least common multiple is the smallest multiple of two distinct numbers. So the least common multiple of 3 and 4, you can actually list them out and have 3, 6, 9, 12. And once you hit 12, well, 4 is 4, 8, 12. So they have the 12 in common, and that would be the number line method of saying, well, look, they both evenly stop here. If we want to use rods, if we have rods, again, that is definitely something that not every school has, but we can work on using rods to show least common multiples as well. If I'm using the intersection of set methods, that would be if I'm looking at these sets that are factors and multiples listed out here. And then I would identify who's in common and who the smallest one in common is. If I want to use the prime factorization method, that means that I'm going to work to prime factor both numbers out. I'm going to then see what we have here in common, and I'm going to take the highest exponent instead of the lowest one because I'm doing the least common multiple, and that would give me my answer. For any two natural numbers, if I take the greatest common divisor and I multiply it by the least common multiple, I should get the same thing as the original product. So if I was doing this, if I wanted to find the least common multiple of this, I could use the Euclidean algorithm or the repeated division to get my greatest common divisor of 17. I could take that, multiply it by the least common multiple, and I should get back to where I started, which would be A times B. So what you're doing here is 731 times 952. If you did the problem right, would give you the same thing as the greatest common divisor times the least common multiple. It's a great self-check, okay? Great self-check. To find the least common multiple of three things, we can start off by looking at prime numbers that it might be divisible by, and using at least one of the given numbers. This is kind of a shot in the dark, right? We're just trying to teach our students strategies. So I could figure out, is 12 divisible by a prime number? Is 75 divisible by a prime number? What about 120? And I can use those facts because 2 doesn't go into 75. I can bring down that 75 and just leave it as is. And to obtain the least common multiple with this, I would continue until the row of answers is exactly relatively prime as the one above. So I would keep carrying down. So 2 divided by 6 is 3. 2 doesn't go into 75, so it's still coming down. 2 goes into 60, 30. 2 goes into 3, doesn't work. 2 goes into 75, doesn't work. 2 goes into 30, 15. Then I'm going to choose another prime number. 3 goes into 3, 1. 3 goes into 75, 25. 3 goes into 15, 5. Well, then I can choose another prime number of 5. And then I finally get 1, 5, and 1. So my least common multiple is the product of the numbers on the left times the numbers on the bottom row.